Okay, so for the first question here, where it's asking you to identify which graph best describes the movement of an object on which no net force is exerted. So what we're saying here is that the net forces on the object would have to be equal to 0 newtons. So the forces would be balanced, which tells us that that object is either going to be at rest or moving with a constant velocity. Okay, so if we look at this first graph, we're seeing that this is an object, the distance versus time graph is curved, which tells me that as each second ticks by, we're not covering the same amount of distance. So this is not a situation where you have a constant velocity. Constant velocity is going to be that straight line showing that the rate of change of distance over time being velocity, is constant. This is showing me a velocity that's actually increasing. As time ticks by, we're able to cover more and more distance every second. These gaps between seconds get bigger and bigger in that vertical direction, telling us that the amount of distance covered gets bigger. This is acceleration here. Here we've got acceleration on this side. Well, clearly there is an unbalanced force here because not only is the object accelerating, but the acceleration is increasing. So the force that's being applied to this object is actually increasing. So there's definitely not a net force of 0 acting on this object. Here we have an object with a constant acceleration telling us that there is an unbalanced net force that is continuously acting on the object. So we've just got constant acceleration, so this is also accelerating. Here we have distance versus time. As each second ticks by, we're covering the same amount of distance. This tells me that the object is moving with a constant velocity, and therefore this is the only graph that represents an object on which no net force is exerted. So this is the only object where that statement is true. So the correct answer here is D. Okay. Now question number 2 asks, if we have two boxes sitting on top of each other, the top one is 2.1 kilograms and the bottom one is 3.5 kilograms. They're asking with what force does the 2.1 push down on the 3.5 kilogram box. So what you've got to understand here is that not only is this 2.1 box going to push down with its own weight, with that 9.8, it's also going to be resisting that acceleration of 1.1 meters per second squared that bottom block is going to have to exert upward on that top block. That tells me that the 2.1 block is going to be exerting a force that is equal to its own mass times the acceleration due to gravity, or rather the magnitude of it, plus that 1.1 meters per second squared. That force is going to be acting down in that negative direction, and overall that should be a negative 23 newtons, essentially, where we're taking the mass being 2.1 times 9.8 plus 1.1. So I'm just going to go ahead and add these two up together first off, and then, truly both of these would be negative numbers because the 2.1 is resisting that push up. That comes from Newton's third law, the equal and opposite. But it also stems from Newton's first law, which, remember, that states that all objects, an object in motion will stay in motion and an object at rest will stay at rest. So this component here, the fact that it is resisting that 1.1 meters per second squared acceleration upward, is coming from Newton's first law. So let's go ahead and we can rewrite this. I'm just going to go ahead and rewrite this down here. So the force of the 2.1 on the 3.5 is equal to the mass of the 2.1, which is 2.1 kilograms, times the acceleration of gravity, which is negative 9.8 meters per second squared, plus that resistance to the 1.1 meters per second squared. We're actually adding those up. And so that is going to be equal to then negative 10.9 meters per second squared multiplied by the 2.1 kilograms. And that is going to be equal to, I'm going to slide that up here, that is going to be equal to about negative 23 newtons altogether.